So, hello. On the combinations, right? So I kind of jump right ahead right now because as I mentioned in the previous lesson, it's better to probably allocate the time to go over these two together. These are somewhat related formulas. Remember in the previous case, we talked about permutation in which we select ordered k objects from n available. Right, the ordering matters. But let's put the motivation for this section in form of a question. What if the order does not matter? So my first example in the previous lesson on permutation, I said, okay, let's say, we have these 4 letters, A, B, C, D, and then form 2 letter codes. But let's flip the script a little bit and let's say we have 4 people, A, B, C, D, and then I just need to select 2 of them for a job, let's say. And so in both cases, the question is, how many selections can you make? Now, in the case in which repetition is allowed, in which ordering matters, repetition is not allowed in both of them. You cannot select more than one. So in the 2-letter codes, ordering matters. Right, so let's write again all the possibilities here to illustrate. So we have A, B, B, A, A, C, C, A. There are 12 of them if you remember. A, D, D, A, B, C, C, B, what was that? B, D, D, B, and then C, D, and D, C. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So this is how many you have, 12, if order matters, right? But if order doesn't matter, and please compare it here with the left column, right? So in this case, ordering does not matter. In which case, A, B, and B, A, it's really the same selection. AC and CA is really the same selection. I selected person A and C. This is really the same selection. BC and CB is really just one selection. BD and DB is one selection. And finally, CD and DC is just a single selection. So clearly, in this case, you have fewer possibilities, fewer selections in total. Right, if the ordering does not matter, right? So that's the key thing, if the ordering does not matter. So the question is, how can I come up with a formula? That's basically the key thing, because we can kind of make an intuitive argument that probably the formula for the combinations can be derived from the permutation. I just have to basically remove the duplicates, if you want, from the permutations, right? I mean, for all the different possible arrangements in each selection, so in both cases I select 2 objects, whether you call them 2 letters or you call them 2 people for a job, I just have to eliminate the duplicates so that each selection counts only once, right? Now, if you look carefully here for each selection, so each time I select 2 objects, there are exactly 2 arrangements or 2 orderings, right? So therefore, the number of ordering selections I can have on the left side, if I divide it by 2, I get exactly the number of selections in which the ordering doesn't matter. So notice that the number of selections in which the ordering does not matter is actually 6. And that can be related to the number of permutations by taking the number of permutations. So you take the number of permutations on the top and you divide it by the number of orderings for each selection. Right? In this example, I always select 2 objects, right? 2 out of 4. And each selection can be combined in 2 ways, can be ordered in 2 ways, right? A, B, B, A, B, C, C, B, and so on and so forth. So these remark basically, which we will probably write it on the second page, so we have it nicely on the top. This basically gives you the insight on the formula for what we're going to call combinations, right? We take the number of permutations in which ordering matters and we divide by the number of orderings so that those different orderings for each selections count only once. Before we move on to the second page, let me remind you again one important observation. If I have k objects, the number of orderings is k factorial. So we established that with the multiplication principle. That's equivalent to the question of in how many ways can you arrange or can you rank, for instance, k candidates or a number of candidates. The same question can be reformulated if I have k objects, what's the number of ordering, right? It's k factorial. Again, that's an application of the multiplication principle, right? I mean, for the first position you have k, the second one less, and so on all the way down to the last position. So notice that these, the fact that 2 objects have 2 orderings is because 2 factorial is exactly 1 times 2, right? So that's why you have 2 possible ways to order 2 objects. And so with that in mind, let's move on to the second page so we can actually define what we mean by combinations, and then we move on with some other examples. All right, so let's write the definition here. The combinations denoted by C n comma k represents the number of ways we can select k objects from n distinct ones. So of course k less than or equal to n, without regard to order. And just like in the case of permutations, repetition is not allowed, right? So you can select the same objects more than once. But again, the key thing is that without regard to order. So like I said before, the way we come up with the formula for the combination, it's just to relate it to the permutation. So if you think about this way, so you can take the number of permutations, right? So this quantity p of n comma k, remember, represents the number of arrangements, right? So again, you select the k objects out of n objects, but you count differently the number of the orderings, right? So the ordering matter. Now, once you select k objects, the number of ways you can rearrange those objects, the number of orderings with k objects is going to be k factorial. So you take the permutation and you divide those permutations to k factorial so that you can count only once each selection, right? So you divide by the number of ways k objects can be rearranged. So that gives you the formula which we use in practice. Because remember, the formula for the permutation is n factorial divided by n minus k factorial. Everything is divided again to another k factorial. And then if you simplify this fraction over a fraction, you get n factorial over n minus k factorial times k factorial. Or you can change the order of the factors. What I like, and let's actually write it here in a box. It's n factorial divided by k factorial quantity n minus k factorial. So you have 2 factorials on the bottom multiplied and 1 on the top. So this is the way the formula is given in the formula sheet. And this is the one to use again when ordering does not matter. You have to pay attention to word problems to see when the ordering matters or doesn't matter. I do want to point out, because I still owe you an explanation why 0 factorial is defined to be 1. So here's an example. What is the combination of n comma n? So what if I have to choose n objects out of n? Pause for a moment and try to answer this question. If you have to choose n objects out of n available ones, and the ordering doesn't matter, in how many ways can you do that? So once again, if I have 5 objects, let's say I ask combination 5 comma 5, right? I want to choose 5 objects out of 5 available. Ordering doesn't matter. How many ways can you do that? So pause for a moment. And if you think carefully, you should have come up with the answer equal to 1. Right, in these cases, there's no other there are no other possibilities, right? If I have 5 objects and I have to select all of them and it doesn't matter the ordering, obviously there's only one way to do that. You just grab all of them. Basically, this is another way of saying mathematically grab all of them. In how many ways can you grab all of them? One way. Or if you maybe you grab them and run, if you do something illegal. Just kidding. So the number of ways to grab them is just 1 because you grab them all. But on the other hand, it's convenient to make it so that the combination n choose n still follows the formula. And so if you apply the formula, then it's going to be n factorial on the top. K is going to be n in this case. So on the bottom is n factorial. And in parentheses is n minus n factorial. So notice that you have n factorial divided by n factorial times 0 factorial. These two cancels, and we know the answer should be 1. And that's why by convention it's practical to make it so that 0 factorial is 1. If we don't make this convention, we will have a separated formula when k is equal to n, and that's annoying. Another combination which is also popping up sometimes in applications, in how many ways can you choose 0 objects out of n? This is sometimes a little bit more confusing, but put it this way, in how many ways can you choose nothing from a given set? Doing nothing is essentially one activity, right? I mean, there's not many ways in which you just choose nothing. So again, obviously this should be equal to 1. And by the same token, it's convenient if we make it so that it still fits the formula on the top. When k is 0, we have 0 factorial, n minus 0 factorial. N factorial cancels with n factorial. Hence, again, it's convenient to make 0 factorial to be 1. So with these examples out of the way, let's actually go over some other non-trivial examples of dealing with combinations. So let's say I want to compute combination of 7, 2, right? I mean, sometimes there is a more elaborate way to read this. When I learned this in my home country, it was like that. Combinations of 2 objects chosen from 7. Or combination of 7 objects 2 at a time. I mean, but these are just variations of the same thing. The important thing is to remember that the second number represents the number of objects chosen from the available ones, which is in this case 7. So following the formula, n is 7, so it's 7 factorial over 2 factorial, 7 minus 2 factorial, 7 factorial over 2 factorial times 5 factorial. So remember my advice to pair the bigger factorials together when you simplify. So 5 factorial disappears, you're left on the top with 6 times 7 over 1 times 2. Simplify again, and that's going to be 21. Let's do another quick one. let's say I want combinations 8 comma 5. Again, according to the formula, is 8 factorial divided by 5 factorial, 8 minus 5 factorial, 8 factorial, 5 factorial times 3 factorial. Obviously, you combine 8 with 5, so you're left with 6 times 7 times 8 on the top, 1 times 2 times 3 on the bottom. Notice that 2 times 3 is 6, which can be crossed out with 6, and you're left with 7 times 8, which is 56. And finally, let's actually go over a couple of word problems in which, again, the fact that ordering doesn't matter, it's actually kind of illustrated or suggested by the wording itself of the problem. So let's do, maybe I'm going to use actually, I'm going to use actually another page. Let's see. I'm going to do another page for the second. I want to do 2 examples. So let's do one here and then the next one on the last page. It's going to be a short last page. So suppose, for example, so that's another example, right? So, and let's actually write it here. So a committee a student committee, for example, contains 6 boys and 3 girls. And let's say there are 9 boys and 5 girls available. And so the question here is, how many committees can be formed? All right, so don't rush this problem because it's not that straightforward. I mean, the computation is going to be easy, but the question is how you set up how do you use the right tools and how you set it up. So a committee contains 6 boys and 3 girls, right? So you have to come up with this type of combination, so to speak. And there are 9 boys to choose from. So these 6 boys can be chosen from 9 boys available, and the 3 girls can be chosen from 5 girls available. So when you think about the way the committee is made, obviously the ordering doesn't matter. There is no suggestion in the problem that the ordering matters. You just select a group of students from each subgroup. But there is also a multiplication principle here, because basically the committee you want to form is going to contain a number of boys and a number of girls. Each of them is selected from a separate group. So it's a multiplication principle with 2 slots. The slots for the number of boys and the slots for the number of girls. Okay, so how many possibilities for each? We know that we should have in total 6 boys and we should have 3 girls to form the committee. And then you can multiply the number of choices because again, you form this committee altogether. Well, since since ordering doesn't matter, the question is in how many ways can you select 6 boys out of 9 boys in which ordering doesn't matter? Well, that's given by the combination n comma 6, right? So 6 boys out of n available, ordering doesn't matter. That fulfills the number of possibilities for the first slot. And this is multiplied via the multiplication principle with the number of girls, which should be 3 out of 5. So that means combination of 5 comma 3, and that fulfills the number of possibilities for the slots for girls. So the answer is combination 9 comma 6 times combination 5 comma 3. Once you establish this, that's the hard part. Now you just have to pay attention to write down the formula carefully. and then simplify, right? So the top is n factorial over 6 factorial times 3 factorial, 9 minus 6, right? And then here is 5 factorial, 3 factorial, 5 minus 3, which is 2 factorial. Now you have lots of options to pair the factorials. Again, pair the bigger ones close to each other. I'm going to pair 6 with 9 factorial. Immediately write down what's left. That's 7, 8 times 9 over 1 times 2 times 3. Here I can cross out 3 with 5, and I'm left with 4 times 5, and on the bottom is just 1 times 2. Do some other cleanup here if you can. For example, get used to do this efficiently. For instance, I have a 2 times 2 on the bottom. That can be crossed out with 4. And I have a 3 that can be simplified with 9, and there's 3 left on the top. So you're left with 7, 8, 3, and 5 multiplied together, which gives you 56 times 15. Finally, that's going to be 840 ways to make this committee. So that's this example, one example I want to make. And like I said, stay tuned for one more example, which actually leads to an additional formula. It's not that important, but you might want to keep it in mind. It's written also in the formula sheet, which can be used in a very particular situation as the one that I'm going to show you on the next page, which is the last one. Okay, so this last example, it's kind of similar to the previous one, but not exactly. It's slightly different. So let's see if we can actually spot the difference here. So let's write it down together. Let's say we have a group of 9 people. So a group of 9 people is going to be formed into committees of 4, 3, and 2 people. Let's see, how many committees can be formed? How many committees can be formed if no person can, so let's see, I'm looking at the problem here. Let's see, how many committees can be formed if one person, or if a person can serve in one committee only. So basically you want to split these people into these 3 committees of 4, 3, and 2 people. What you have to notice here, so let's put this as a remark. Notice that 4 plus 3 plus 2 is equal to 9. So this suggests that basically all will be involved, right? And then they will just basically be grouped into these 3 committees of 4, 3, and 2 people. So this leads to a different formula, which is written as a different formula, a different type of permutation. I sometimes hesitate to put that new formula, but I think since I don't require any memorization, I put that in the formula sheet as well. You technically don't need to, because if you understand how combinations work and how the multiplication principle works, then you can do that problem straight away the way I'm going to show you here. So why do we need multiplication principle? So again, remember, you're going to have essentially 3 slots together, right? So that's going to be the 4 people committee. So the 4 people committee. This is the 3 people committee, and then the 2 people committee. All right, so let's start with the first choice here, or the first slot. In how many ways can you fulfill the number of in how many ways can you form these 4-people committee? Well, remember we have 9 people to choose from. For this committee that we select, when we select 4 people out of 9, ordering doesn't matter inside each committee. So obviously the answer is going to be combination of n choose 4, right? So we choose 4 people out of n. But pay attention now when you move on to the 3-people committee, once you fulfill the first committee, you have 4 people less to choose from when you move on to fulfilling the second committee. If you had n people in total, 4 less, you're left with 5 people. So these 3 people have to be chosen from 5 available. So that means combination of 5 choose 3. And then moving on, once you fulfill the first and the second committee, there is only 2 people left, obviously. So you have to choose 2 people out of 2. That's going to be just 1, obviously. One way to do that. I'm just going to write that as a combination just to see the pattern, right? So now there are 2 people left. You have to choose 2 of them. But again, if you remember that this is equal to 1, the last piece there can be skipped if you want to. So multiplication principle, but with the caveat that when you move on to the second committee, you got to take into account that you have fewer and fewer available people as you move along to the second and the third committee. So when you multiply these combinations, you will see the structure of the factorials looks in a very specific way, which leads basically to an additional formula. So if we multiply these combinations, and just for the record, let me write down again the formula for the combination to have it in front of us over here. So combination n choose 4, that's n factorial 4 factorial times 5 factorial. Then 5 factorial on the top, 3 factorial on the bottom, 5 minus 3 is 2 factorial. Finally 2 factorial on the top, 2 factorial on the bottom, 2 minus 2 factorial, which is 0 factorial, which is 1. So notice that the second factor on the bottom is always the first, is the one on the top, on the next one, like that. Again, 0 factorial is actually 1. So you end up with 9 factorial on the bottom, divided by 4 factorial, 3 factorial times 2 factorial. So if you look at the beginning, you had 9 people to choose from, which have to be split into groups of 4, 3, and 2. Basically, you get this nice pattern if you want, formula if you want, with the factors 4, 3, 2 factorials on the bottom. So we're going to write that as an additional formula, but for now, let's actually let's do the simplification here. So I'm gonna again pair the bigger factorials together. So if I cancel 4 factorial, on the top I'm left with 5 times 6 times 7, 8 times 9. And then expand the factorials remaining. And then try to pair what's left kind of efficiently. 1 times 2 times 3 is 6. I can cross out 2 with 8. That gives me 4 on the top. So you're left with 5 times 7 times 4 times 9. 35 times 36, which gives me 1260 possible committees. So I'm going to end up with this additional formula, which you can keep it in mind. But again, keep in mind that it's applied only in a very specific situations, when all objects involved should be split into subgroups in which each subgroup is treated the same. So there's no basically distinction and ordering that matters in each subgroup. So this is called permutation of 8 objects. So let's write it as a definition. So there's no special notation for this, just a formula. So the permutation of n objects of which n1 are of one kind, that'll be basically one committee in the example, and 2 are of the second kind, dot 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 n sub k are of the kth kind, so it sounds kind of weird, so a different kind, with the property that the summation of these is always n. I kind of hate this formula because it in the abstract form looks kind of more complicated than it is in reality, but that's the way it goes, right? So permutations of n objects of which n1 are of one kind, n2 are of a second kind, or a different kind I should have said, and nk are of a different kind, and then the summation is equal to n, is, so that this number of permutation is n factorial divided by n1 factorial, n2 factorial, dot dot dot, and k factorial. So like I said, this only applies when you split this into subgroups, right? So here's another example. If you want, you can check it with the calculator. Let's say you have 15 people and you want to form committees of, let's say, let's do actually 4 different types of committees. Let's say 7 people, no, let's say 6 people, 5 people, 6, 5, let's see, I have 11, right? So up to 15 people, 2 and 2, 2 people and 2 other people, right? So we have to split it into 6, 5, 2 and 2. So you want to form 4 committees, 6, 5, 2 and 2. As long as the summation of the members in each committee is 15, right? So we have 11 plus 4, 15. Then the answer is going to be 15 factorial. And again, assuming that each person serves in one committee, right? So without repetition. So 15 factorial over 6 factorial, 5 factorial, 2 factorial, 2 factorial. And then you just have to use the calculator and some simplification. So in fact, let me actually do this with Wolfram Alpha so that I don't have to do too much work. So we have 6 factorial, like I said, 5 factorial and 2 factorial multiplied twice. Six, 5, 2 and 2. And let's see what we have. We have a big number as expected, 3,783,780. Okay, so again with Wolfram Alpha. And you can check to see that the answer is correct. So with that in mind, we have only one section for this chapter in which we again make use of these formulas, the combinations. And that'll be everything we need to know on the topics of probabilities. We'll still get to talk some probabilities toward the end of the class when we talk about Markov chains. But the heavy stuff on the probability, basically, it's over once we finish the last section of this chapter. So I'll see you next time.